Okay, welcome everyone. Welcome to the presentation on GR CUDA. In this talk, you're going to hear how we can use CUDA and more general NVIDIA GPUs from within the Graal VM. So this work is a joint collaboration between Oracle Labs and NVIDIA. My name is René Müller. I'm a developer technology engineer at NVIDIA. So this talk will be starting out very basic with accelerated computing, kind of high-level overview, and then we're looking into the motivation for why Graal is interesting. Graal VM is interesting platform to look into the GPU integration in modern languages, and then at the end we'll have two demos that hopefully will run now in this setup here. Okay, so in a nutshell, it's about accelerated computing. So what's accelerated computing? And many companies are now looking into accelerated computers because they made a simple observation. That's shown here in this plot on the right, in this blue curve that shows single thread performance over the years, and it can be, you can see that in this exponential plot at some point the single thread performance has plateaued out. That does not necessarily mean that Moore's law stops, right? You can still put more cores and more logic on the chip, and that's what's illustrated in the green line that's imposed on top. That shows the aggregate performance, compute performance of the die, or GPU die, right? So that keeps on going for a while at least. And you also see this happening in regular CPU cores, that the number is growing. The difference here is that if you are starting out in an architecture that's inherently parallel, has been built for parallelism in mind from the ground up, then it becomes easier to scale it out. Now for the applications perspective, you really want to be, traditionally want to be as close to the metal as possible. And then you want to make sure that you have full stack optimization, making sure that the operating system with the driver and data exchanges happen very efficiently. You want to make sure that you're using the right algorithms for your problem all the way up to the application. That's what gives you accelerated computing in the end. So what are the benefits? Well, here is a kind of back on the envelope calculation. You can get GPU instances by cloud service providers. Here's Oracle as the example. You can get two instances, one a CPU instance and the other one a GPU instance. Here I took as an example. You can see a difference in the cost, in the compute cost. But the idea is that if you happen to accelerate your application in such a way that you exceed this price difference, you can actually start saving money. And in the end, with these examples I will show at the end of this talk, we actually achieved this performance speed up in that case. So if you really would do the math from a financial perspective, you can actually end up with savings. So what does it actually mean to do accelerated computing? Well, the ideal case is you start out with the application code, and you not trying to run all the application code on your accelerator or on the GPU. The ideal case, you identify a piece of code, a small piece of code, maybe here 5%, where you spend most of the time, right? Then you take that piece of code and you port it onto the GPU, while you leave the rest of the computation running on your regular CPU core or cores. What you end up with is a heterogeneous computing platform, so you have to deal with two sets of instructions, one for the GPU, one for the CPU. You have to make sure that you schedule the execution in the right way, that ideally you keep both devices busy at the same time, so you can actually take advantage of this parallelism. And essentially you need to, it's a question of synchronizing the work across these two devices. That's the one side of the coin. The other side of the coin is worrying about data. As you may know, GPUs have local memory, device memory, attached to them that provides bandwidth in several hundreds of gigabytes per second. And you would like to use that local device memory as much as possible to take advantage of this high bandwidth memory. Now, for that to work, you really have to be careful about data placement. Specifically, you want to make sure that the data is really accessed mostly on the device memory. Now, a couple of years ago, we introduced a concept called unified memory that, you as a programmer, gives you an abstraction, unified abstraction of that memory, and one single memory space, and you can exchange data between the device and the host, the CPU cores, through that unified memory, and you let then the driver, the operating system, or the runtime taking care of the data movement. Right? That will become later on during the talk, but I want to highlight this already here at this point. So how do you program GPUs? Well, our way to do it is through CUDA, which is at the heart, it's a C++ language extension that allows you to write host code and device code within the same compilation unit, like shown here on the right. The blue box is CPU code. The green box is a function that is run as a kernel on the device. And you see, this is C. Looks like C. There are pointers there. You have to allocate memory, and then you invoke that GPU function like a regular function with a bit of an odd syntax decoration. Yeah? So the ecosystem itself is fairly mature over these years. It's not only the language itself. There are compilers, debuggers, profilers. There's even a device-side printf that you can use to do debugging. There are also a bunch of accelerated libraries, like CUDA-X libraries that are shipping with this platform. Right? This is all happening at a fairly low level, but that's the way how you would go and write your high-performance applications if you want to be as close to the metal to get the maximum performance out of the hardware. Now, if you look at in the broader scope of programming languages, we see that this is from a recent study done by IEEE Spectrum about the popularity of various programming languages. This is, I think, the survey was done for engineers, maybe enterprise application developers. The relative order would look slightly different. But the key here is that the high-level languages are really on top. Python, Java, but also R. JavaScript is next. So people would like to program in higher-level languages. But that doesn't mean that there are no GPU bindings for those languages. On the contrary, there are many of those bindings. Like even Python has several of those. And they vary in the terms of the functionality they provide. Some are thin wrappers around our API. Some have higher level of abstraction with code generation and so forth. Right? So we are at this point, just to make it clear, we are not saying that GRCUDA will replace those languages. Those languages will stay. So what we did in the context of GRCUDA and the Graal work was, okay, so once we have a platform such as Graal VM, what could we do to rethink the binding, the GPU binding for those languages? Right? That's really the key motivator behind that. So what we want to do is first of all making it easy for the programmer to use the GPU. To expose memory of the GPU. So, for example, if a programmer wants to go and see under the hood how things work at a low level, we would also like to provide this kind of a low-level access, while providing as well at the same time also high-level abstractions. And then a key feature here is really the plumbing work, right? There are a lot of X-related GPU libraries out there, and what we want to do is not necessarily generate code, new code that runs on a GPU, but allowing high-level application developers to leverage this existing GPU library. So it becomes then, rather than a code generation issue, it becomes a plumbing issue. Point number 4, it was still also to allow programmers to, when necessary, to write GPU kernels through a way that's kind of looks similar to what OpenCL does with user level or application level strings that can be compiled at runtime. And finally, the interface, this binding should be uniform across all those Graal languages. Just having this the opportunity of the Graal ecosystem, so that any new Graal language, Graal-VM language that comes into the environment can automatically take advantage of the GPU without having to implement, without the language designers or implementers having to implement their own GPU binding. That's the goal of this approach. And as the key inside of that, this solution here is that GRCUDA is nothing else but a truffle language. So a language that's implemented on the truffle framework of Graal-VM. So let me give you a brief overview of Graal-VM and the Graal-VM ecosystem. In that context, as we are discussing it here, it starts at the JVM hotspot layer, where the hotspot JIT is replaced by a new compiler, the Graal compiler, that is written in Java and interfaces with the hotspot VM through the compiler interface. So in that case, it allows all Java bytecode-based languages directly to run on top of this Graal VM at the VM level. But there's another component that sits on top, which is the Truffle framework. It's a language implementation framework, and essentially it simplifies the effort for language developers to implement fast interpreters. In fact, it's sufficient to implement your language as an interpreter against this Truffle framework, and then you get an optimizing compiler for free. That's all being abstracted in this framework. And there are a couple of languages that are already available in this Graal-VM, so we call the Graal-VM languages, such as Python, Node.js, R, and Ruby. There's also a possibility to integrate LLVM based languages. That means languages that can compile, native languages that compile into LLVM IR, intermediate representation. They can go in through the Sulong component. That's brief in a nutshell what Graal-VM is all about. And now the next kind of components really that matters for GRCUDA is the Truffle framework. So this is taken from Wimmer's presentation, One VM to Rule Them All. This is the PLDI 16 tutorial, and this is this polyglot diamond. So what matters here is that this works within the Graal-VM, and the languages are implemented all on the top of the Truffle framework. And now the key observation here is that objects can be shared across language implementations, across language interpreters. So what that means here, for example, you can create an object in R, export it, and use it in JavaScript. So that's the yellow ellipse that you can see here. And we do the same thing with GRCUDA. Specifically, we have objects in GRCUDA that refer to device resources that then can be shared between the different Graal languages. So here is a simple example how this would look like. So this is nothing at this point, nothing to do with GRCUDA yet. This is regular polyglot operations within Graal itself. So we are starting with in a Node.js environment. So we are firing up Node. And then we have this polyglot object that we can ask to evaluate an expression in a different language, a foreign expression if you like. And so the first line, we are asking it to evaluate the Python expression, and the Python expression you see there on the right, and this sums up all odd numbers from 1 to 100. It's a Python generator expression. You can do the same thing in R, just you specify a different language R, and then you have the equivalent R expression here. The expression will be evaluated in that corresponding language, and what we're getting back is a scalar value here. That's the sum, and then hopefully that sum is then being passed out to the JavaScript world, and we can compare whether these languages, whether these values are equal. Right. So this is the regular approach. What we can also do is, let's say we're still in Node, and let's say we want to use a random number generator, but for whatever reason we feel like we want to use a random number generator from R. So we can use it as follows. We can just invoke the function directly as an expression in R, and then we're getting back as a result the random number. What we could also do is we can drop the parentheses, and then what we're getting back is not the value of a random number, but we're getting back the function itself as a callable object. And then we can pretend that this is a regular JavaScript function which we can simply invoke. All right? And we can also invoke it differently. If you invoke it with 10, we're getting 10 numbers back. So also an interesting observation is this is all dynamically typed as common for these high-level scripting languages. So the result here is rather than a scalar value, is an array. And so that's what we're making use in grCUDA. So grCUDA is pretty much follows the same architecture diagram here as any other Truffle language. It's built on top the Graal compiler, and it's implemented against Truffle. It's implemented in Java, and it can be used by any of the other Graal languages. So what's new? It has on the other leg, so to speak, it's tied to the CUDA runtime, and we can link in external native code, either a native host code that makes use of the GPU and uses GPU device pointers, or it can also be directly GPU kernels themselves that have been compiled ahead of time. Yeah? So it allows us to bring in this existing code, this existing native code that comes from these accelerated libraries that these high-level, let's say, Node.js developers would like to use. And a way to exchange data is through an abstraction, a memory abstraction, a device array abstraction that the host application, the host program, the high-level program can exchange data with the kernel. And as I said before, there's a mechanism that you can compile GPU kernels from host language strings, so you could have a JavaScript string and compile it into that contains a CUDA program and compile this into a kernel. Right. So here's again coming back to the unified memory. Currently, these device memory, device arrays are backed by managed memory. So for those who program CUDA, this is a CUDA malloc managed memory. And so right now we're only supporting primitive types at the moment and flat arrays in this array. But the key here is that this is pageable memory, so it could also be oversubscribed. Yeah, and the host and the device can both page fold into this memory, and the page will be moved around. This happens on all recent GPUs like Pascal and Forward. Yeah. So there's also a possibility that you can set a device. For example, let's say the GPU is only accessing the memory read only, right? Then one can provide that device, and then the a copy of that page will be made on that device. At some point, all the entire, if it fits in the device memory, you will have all the entire pages of the device array on the GPU device. Okay, so that's the idea. So we have a mechanism to create code, to invoke code, and a way to exchange data. So let's see how this actually looks in practice. So we're switching over from JavaScript to Python. So in Python, I need to bring in the polyglot binding through the polyglot module package. And the first thing I'm doing, I'm extracting a device array constructor. So this is the second scenario that we had before. Remember the random number generator from R, where we dropped the parentheses. We're doing exactly the same thing. We're getting back a callable object back to Python, which you can then invoke, for example, to create a homogeneous array, one-dimensional array that may be able to hold 1,000 elements. We can do multi-dimensional arrays. There's also an option to specify the ordering between C ordering and Fortran ordering in case you have HPC code that will require BLAS routines. You can specify that if you want to have a different ordering. And then you can access this array, pretend this is a regular Python array, or more specifically a Python list, through the bracket operator. If it's a two-dimensional array, well, two-dimensional array doesn't exist as first-class citizen in Python. There are lists of lists. So what you have to do, you have to dereference it once, and then have a second array access on that starting from the first access. Yeah? And here, what looks like terribly slow and terribly inefficient, because we need to create essentially a view from the first axis and then accessing that view for the second J axis, this is not actually slow. The reason is, and that's where GraalVM, the Graal compiler, comes in. We're taking advantage of optimizations that the GraalVM compiler, the Graal compiler, can do at this point. And I tried to illustrate this in this performance chart. So this is testing arrays that can hold 16 million entries for 4 different languages: Python, Node.js, Ruby, and R. And I'm testing 3 configurations. One-dimensional array, so that's the light green one, so that's 16 million entries. Then there's the dark green one, is 4K times 4K elements. And the gray one is 256 times 256 times 256, so a 3-dimensional array. And then I measure the performance speed up that the device array achieves over the corresponding native array access. And here native, I mean the native array access that is native in that corresponding language, like a Python array. In that case, I'm using the typed version of the Python array, the Node.js array, and the R vector. Yeah. So here, in many cases, it's actually faster. That's not entirely surprising, given the fact that the array itself is homogeneous, right? There are cases where it's slower in Python, notably in Python, and slightly in R for the one-dimensional case. It's not entirely clear where this is coming from. We're looking at this with Oracle. The net effect of this slide is really, even though we have this high-level abstractions of the array access, it's not necessarily slower, right? It's virtually at the same speed at this point. So that's really advantage that the Graal compiler actually brings into this picture over here. Okay, so this is talking about the data itself, how to exchange data. So let's turn on over the other side of the coin. Let's look at how we execute code. So here, this is in a nutshell how a GPU kernel could look like. It's here shown as a templated C++ function. It's a regular function, except that it has this dunder global dunder identifier in front of it. You see it takes pointers What this function essentially is doing, it takes an array, adds 1 to it, and stores the result in another array. It's doing this all out of place increment essentially. And the way this code executes is in the form of a computation of a compute grid. It's a number of thread blocks, and each thread block contains a number of threads. The reason for that is that we provide efficient synchronization and coordination mechanisms and data exchange mechanisms between threads that were within the same block. Yeah. So the first thing that this code is doing, it's figuring out, okay, where am I? So each thread essentially is executing that function on the GPU, and it will figure out I'm in block such and such, and giving me the absolute block offset, and then the intra block offset determines the index, and then we loop over this in this idiomatic CUDA for loop. So that's the kind of kernel that we try to run. So how do we get this when we write that kernel? There are a number of built-in functions in grCUDA that you can access. So on one of these functions, build kernel, it takes a string. The name is the kernel source code itself. The second argument is the kernel name, the name of the kernel symbol, and then the third is the kernel signature. The kernel signature is a truffle native foreign interface string. We're using the same signature, and that is needed to bridge the high-level dynamically typed environment with the statically typed native execution in the native code. So we could potentially infer the signature from the kernel signature. We are not doing that at this point for simplicity reason, as we don't really want to have a template deduction engine figuring out the signature, because the types of the function or the kernel might be template parameters. And the supported types are uint8s, the signed versions of the floats and double. In accordance to the NFA interface, the kernel signature itself is non-typed, so the initial pointers that we had before become just untyped pointers. So and now we can take that string. So here is a multi-line Python string of the kernel call build kernel, which then invokes the runtime compiler. That's part of CUDA, and which in turn then generates some platform-independent execution instructions. It's like a virtual ISA, which we can then load into the driver and then execute, then load that corresponding code. What we're getting back is a function, a callable, a kernel truffle object that we can we can launch then, right? That's kind of shown here. The kernel launchable or the kernel callable is a function with essentially two argument lists. The first argument list contains the kernel grid configurations, how many kernel blocks, how many threads per block are we using. The second argument list contains the arguments that we're passing over to the kernel. So here's how it would look in R. We have the grid size and the number of thread blocks per threads per thread block is the block size. That goes into the first argument in green, and then the second argument list is are the kernel arguments. So we did this to keep the syntax in par with the regular CUDA C++ launch syntax with this triple angular bracket notation. So we also support the same 1, 2, or 3-dimensional arguments for grids and block sizes, as well as dynamic allocated shared memory. Now, this execution right now in this early prototype is that the kernel execution is synchronous. So that means that the host will have to wait until the kernel has terminated or is complete. We're gonna talk a little bit about that later on in the future work part of what the next features we think of implementing. Now, here's a concrete example in JavaScript. So we start with the green part is the kernel, is increment kernel, is now as a JavaScript template string, contains the templated CUDA kernel. We get the first line below, we get the build kernel function out of grCUDA, then we invoke the function, essentially meaning we build the kernel. That's also where we would get the compiler errors in the same way as you would get the compiler errors for the regular CUDA compiler. We can specify the template instantiation here. We can say the T becomes a float, and then we have the actual kernel object that we can call. The next thing, maybe on top, we create a device array for the input and the output. We fill the array with this for loop, and then finally we can launch that kernel on a grid that's 160 thread blocks, each having 256 threads. Right, and in the end, we can print out the first 10 elements from the result array. So the idea here is really we want to write as a little boilerplate code as possible, just to allow users to integrate their GPU kernels into their high-level code. The other side of the plumbing is that maybe you want to leverage a function or a library that is already optimized with GPU acceleration. And so you can use the bind function. You can bind to a specific symbol in a shared object. You also specify the function signature. This is the same as the Truffle native foreign interface. The difference here is that if you pass this function a device array object, then grCUDA will know that this is a device array and will automatically unbox the underlying pointer. So we don't have to pass around pointer ever in grCUDA. Right? If you pass a device array object and the function or the kernel expects a pointer, then it would, through the Truffle interrupt library, would automatically extract the underlying pointer. Same happens if you want to access a pre-compiled kernel. You can refer to the kubin or the PTX code. You specify the kernel name and also same the kernel signature, and then that is referring to directly invoking the kernel as opposed to invoking host code that will in turn some point later invoke one or more GPU kernels. Okay, so I think at that point we can switch over to some demos. So the first demo I'm going to show you is a demo from R. And what we're doing here is we're invoking a machine learning function, specifically UMAP. It's a manifold learning algorithm that's been very popular since last year, that we implemented in Rapids QML. This is the Rapids accelerated machine learning library called QML. And what it's doing is the following. We're taking the Hello World data set, so the MNIST data set. These are 60,000 images, 28 times 28 pixels per image. This amounts to, if you flatten this out, amounts to 784 dimensional vector. And we want to figure out, can we somehow cluster it onto 2 dimensions so that we have odd points that correspond to the same handwritten digit in the same space. And that's what UMAP is good at, is doing dimensional reduction. That's better than random projection because it preserves a local and global structure. So what you end up then, if everything works out fine, you have a ggplot2 plot that shows these 2 clusters. Shows these 2-dimensional image with the corresponding 10 clusters. So how does this work? Well, we start with the Rapids library. Essentially what we're interested in is the libqml SO, and there's a C binding for it, called libqml. And Rapids is implemented with its current form, has a regular Python binding, so it's implemented. That is implemented through Thyssen. So that's the gray box around here in the right. That's what currently ships in Rapids for QML. Now, what we can do here with the bind functionality is we can use grCUDA to directly access that API here. And what grCUDA allows users to do is to pre-register some of that function. So it defines a name. For example, here it defines a namespace ML, and then it maps signatures from all those functions into that namespace. That has to be done manually, but this only needs to be done once, and then you have that registration set up. And then you allow any program written in a high-level language, such as Ruby, Node.js, or R, besides Graal Python as well, to access this API. Okay. So let's see. That's how the code looks like. But let's see code talks better. Let's switch over here to the terminal. So I start. You see here. This is the regular R interpreter. And I have a UMAP package that runs here on this. I'm showing this on a laptop, and I'm running only 4,000 images just to keep the time low. And the code now for QML looks like as follows. The data comes in a data frame. What we need to do here, because the library. The UMAP library expects it as a two-dimensional matrix. We need to flatten this out in a two-dimensional matrix, which at this point we have to do it manually. There's a future work. We have ideas how we can automate this through a declarative interface. So yeah, the computation is done. We see the first clusters. Let's go back here. So it took us about 35 seconds to do this on the CPU. So let's see what the GPU can do. Run the same thing again. So with all the warm-up work, we can do it in the same thing in 3.5 seconds. That's really running on this wimpy laptop GPU that I have here with 2 processors essentially only. So you can do that in 3.5 seconds. Okay, and here you see the corresponding scatter plot. And the invocation is fairly straightforward. We can go back to the code. We get the constructor function out to create those arrays. We extract a callable from the UMAP fit function from Rapids. We created 2 arrays. One is the two-dimensional matrix that we use that holds the input images or the input vector. We copy them over from the data frame that we loaded before. We invoke that function here. This function actually goes into the Rapids code. And then at the end, we're getting the result in this two-dimensional projection, and we copy that back into something that we can visualize in ggplot. Right. So even though there's no R binding currently in Rapids, right, with grCUDA, you can use the accelerated libraries such as QML in R. The next use case maybe is this Mandelbrot fractal that we want to run from a simple Node.js web app. So this is more about ease of use rather than performance. The idea here is to show that you can do this with less than 100 lines of code, and to compute that kernel, that image directly in a single Node.js application. Right, that's kind of shown here. So that includes So it's a 106 lines of code, and that includes the kernel. The entire kernel is shown up here. It's a Node.js application using the Express.js web framework. We have here our kernel that iterates over the image, and then there's a special another device function that I used to compute the colors for that. And then you can see here the route. The route extracts from the web server, extracts the center points and the width and height of the window, and then computes that fractal. I'm using Pillow. I'm using not Pillow. I'm using a GIMP to express to represent the image in the end. Okay, so let's run this. Let's close this out. This is the Node app that you've just seen. So JirCuda comes up, and as soon as it's ready to listen on port 3000, I can point the browser here. Obviously, there's some browser level side just to draw these things, but that's not it's not included in this 100 lines of code. The 100 lines of code are simply referring to the backend code. So the kernel is already complete. It takes a little bit initially for GraalVM to warm up the Gimple code. So you see in here the latency of that first call was about 8 seconds. If I zoom in here first for the first time, we're down to 2.8 seconds, and I think as Graal gets warmer, you see this time goes down. Okay, and the key over here is not necessarily the performance. The key here is really that this can be done. That's the entire code that does this. Okay, switching back to the slides now. So how can you get started? So JirCuda is open source. You find it on GitHub. It's licensed under a BSD 3-class license. So you need to install GraalVM. The community version is fine. Then you go to the release in the JirCuda. You copy the jar file, and it's sufficient just to drop it into languages JirCuda in your GraalVM installation. So we are very interested to see what you can do with this and future application. That would also then direct us in which way we could extend JirCuda. So if you try it out and you have bugs, feel free to submit them as issues, or also if you have feature requests, feel free to contact us. So what's next? So what the next things in the pipeline is device memory that's being managed explicitly through explicit device transfer. I think we can be much smarter by if you have a pipeline of computation where we can overlap transfers and computation, and we can better manage these memory transfers without having to expose them to the developers. That also then allows us to do asynchronous execution of copy and kernel operations. So the model that we are thinking of is an eager asynchronous execution model. So it's different than CUDA graphs, where you have to see the whole graphs until the end of until you freeze the graph for an execution. Here we would eagerly execute the kernels asynchronously as soon as the data dependencies are met. The last thing is the format conversion and shredding of host language objects. So mainly it's this data transfer conversion. So here's maybe a simple example. Let's say you want to train a classifier for loans, or use for defaulting loans, and your enterprise application has this loan data in Python object, in a list of Python object or Node.js sitting somewhere that you pull out from some database in a high level and turn them through Hibernate or whatever technology into high level language objects right? And then the other end, we have the GPU acceleration, the XGBoost, that would require a D matrix, and we have to convert essentially a list of Python dicts into something that is just consumable by XGBoost. And we're looking into how we can transfer and convert this using a declarative interface. Yeah, so that's all I had. So to summarize, currently it's a research prototype as a collaborative effort between Oracle Labs and NVIDIA. It is open source. All is on GitHub. Also, the new features will be on GitHub as we're building them. The key here is to expose the CUDA environment or CUDA platform to GraalVM, and we're really we're able to take a couple of techniques from features that GraalVM provides to make to take advantage of that in GRCUDA. That means also all languages are supported, also possible future languages, and we have essentially two aspects. One is handling device data, and the other one is exchanging code. Yeah, that's all I have, and give it a go, try it out, and let us know what you think about it. Thank you very much.